Diving in Hyperbaric Physics by Dr. Frans Cronje. There are many unique things about diving, but amongst others, perhaps one of the most important is that it occurs in a non-breathable liquid, water. This is important not only because it introduces several safety hazards, but also because the ambient pressure increases quickly and dramatically and necessitates gas breathing under increased pressure also. Much of physics is understanding how to manage, prevent, or deal with complications arising as a result of these two factors. This basic physics introduction will consider buoyancy, the gas laws, Laplace's equation, Poiseuille's equation, and Pascal's law. To start off with, buoyancy. Buoyancy is part of the pleasure and sometimes part of the pain of diving. Archimedes, a Sicilian Greek born in Syracuse, is credited for our understanding of buoyancy. In simple terms, Archimedes' law says that when a body is wholly or partly immersed in a fluid, it experiences an upthrust or a buoyant force that is equal to the weight of the fluid it displaces. So, if the object weighs less than the volume of water or fluid that it displaces, it will float or be positively buoyant. Conversely, if it is heavier than the equal volume of water, it will sink or be negatively buoyant, and if it is the same, it will be neutral or neutrally buoyant. Now, divers have their own specific gravity, and in addition, they wear equipment that influences their buoyancy. The most notable three are the wetsuit, which frequently is a buoyant neoprene sponge, a wet belt, which is meant to offset the buoyant effect of the wetsuit, and a buoyancy compensating device that allows them to adjust buoyancy on demand. However, there are many other factors that influence divers, and each of these may have safety implications. The ideal state of divers depends on the reason for diving. In recreational diving, the idea is to stay off the bottom. Commercial divers would frequently be tethered or weighed down to be able to remain stable on a platform or on the bottom. So for recreational divers, they should be neutrally buoyant, avoid damaging the reef. They should maintain controlled changes in buoyancy during ascent and descent. And finally, upon reaching the surface, they should be positively buoyant. In other words, they should remain afloat so that they can be retrieved or returned to whatever platform they were diving from. So much for buoyancy. After a wonderful 9-month apprenticeship of liquid breathing on cardiopulmonary bypass, we are sadly born into an ocean of air and doomed to breathe gas for the remainder of our lives. This ordained physiological requirement to breathe gas is the single most important contributing factor to the complexity of diving medicine. Were it not for the fact that we needed to increase the pressure of gas that we breathe to balance the increasing pressure of the surrounding water, many of the physiological barriers and consequences of diving would be fairly simple and uncomplicated, and they would certainly be far more benign. But our gas spaces and their response to compression, decompression, and gas transfer determine our need to understand the physical aspects of diving. So when it comes to the gas laws, the ones that are most important are listed here. We won't spend too much time on the ideal gas law, but rather focus on the general gas law and its derivatives, those of Boyle, Charles, and Gay-Lussac, Dalton's law, and Henry's law. What is important from a diving medical point of view is to have a functional understanding of what the law entails and then how it applies to divers, not only physiologically, but also if they're suffering from some medical condition or if there are equipment considerations, for instance, treating a diver under hyperbaric conditions. When it comes to understanding the gas laws, there are essentially 4 core concepts. And to start with, there are also 4 variables. There is pressure, volume, and temperature of the gas, as well as the actual number of gas molecules. It's important to keep track of those variables because in certain situations, one or more of those variables may actually be unchanging, and therefore a simplified version of gas laws may apply. This will become clearer in a moment. The second important consideration is that one has to use absolute values for temperature and pressure. Just to summarize it here briefly, temperature occurs on an absolute scale, but most of the familiar scales like centigrade or Fahrenheit do not record absolute zero. It's not as cold as it can get when you are at 0 degrees or 0 Fahrenheit, so one needs to convert those scales to absolute scales. The same with pressure. Most pressure measurements occur with gauges reading zero, even though we know they occur in atmospheric pressure. So again, we need absolute pressures, and it's a common mistake to omit those. The third element is understanding whether or not the actual number of gas molecules within the gas system that is considered has changed. If gas has been added, you cannot use the general gas law because that's a comparative law of the same number of molecules in different states of pressure, volume, and temperature. So then, if they have changed, you need to use the ideal gas law. Lastly, and as a simple mathematical principle, the values need to be labeled correctly and the same units of measure need to be used throughout or converted in a way that they can be used consistently throughout. When it comes to the application, the gas laws largely predict the probability of damage, for instance to the ear, sinuses, even the eye or the lungs, whether there will be deformity in the form of equipment or gas spaces, whether there may be discomfort as a result not only of the pressure changes, but also temperature changes or humidity and condensation, and lastly, whether there would be particular dangers of depth, of which oxygen toxicity, nitrogen narcosis, decompression sickness, gas density issues, and high-pressure nervous syndrome are perhaps the most important. Let's take these one by one, and we'll start by looking at the four variables of pressure, volume, temperature, and gas molecules. Imagine the two columns you're looking at here as being made up of the same substance. It doesn't matter whether this is water or wood or metal. And the question is, which would exert a greater pressure? Now, there is an element of logic into thinking that the greater one, or the larger one, would conceivably exert a greater pressure. It is true that it represents a greater amount of force, but what needs to be realized is that that force is now distributed over a proportionately larger area. And therefore, the pressure is actually the same, because the force, or the weight, per surface area is the same. And for that reason, we can say that 14.7 pounds per square inch is the same pressure as 1 kilogram per square centimeter. Let's look at this now in the context of atmospheric pressure and hydrostatic pressure. 1 atmosphere is the total pressure that is exerted by a column of gas from space to sea level. This is equivalent to the hydrostatic pressure at 10 meters in the sea. In other words, we fly in fractions of atmospheric pressure, but we dive in multiples of atmospheric pressure. By 10 meters, the ambient pressure has already doubled. We therefore, when we consider gas calculations and gas laws, need to consider absolute pressure, and that means adding the atmospheric pressure to whatever the hydrostatic pressure is. A common term that delineates only the hydrostatic pressure is gauge pressure, or perhaps relative pressure. So let's consider hydrostatic pressure. But the reality is that it doesn't happen. And the question is why? The answer is that hydrostatic pressure is a function of vertical height of the water column only. In other words, It doesn't matter how much water there is, it matters how deep you are in the vertical dimension. We've already mentioned that absolute pressures must be used when doing gas law calculations. Here are some common units of pressure that you should be familiar with. In terms of absolute pressures, there are atmospheres absolute, pounds per square inch absolute, millimeters mercury, and kilopascals, but only the first two are unconditionally absolute pressures. In other words, the term itself defines that they are absolute pressures. You recognize them as ATA and PSIA. The other units are not necessarily absolute. On the gauge or relative pressure side, there is ATM, which again is designated as a gauge, relative, or a mechanical pressure. Pounds per square inch or pounds per square inch gauge, PSI or PSIG, and in certain cases millimeters mercury, bar, feet or meters seawater, kilopascals and megapascals. Note that millimeters mercury could be used interchangeably as an absolute or a relative pressure. An example might be barometric pressure, which is absolute, versus blood pressure, which is mechanical. When we convert units of measure, it's important to understand how we change from absolute to absolute, absolute to gauge, or gauge to absolute pressures. In this example, you can see that column that we showed earlier on. Imagine that the part that is suspended outside of the sea level portion as representing atmospheric pressure, and then a certain amount of hydrostatic pressure below it. So in this case, to convert, for instance, 14.7 pounds per square inch to kilogram per square centimeter, it would be a 14.7 to 1 conversion. You would simply divide PSI by 14.7. However, that would give you a result that is still in absolute pressure, because we started with an absolute pressure. To change that to gauge, we now need to subtract the atmospheric pressure in the same units of measure as the target unit of measure. If we go from gauge to absolute, in this case, we would first need to add the atmospheric pressure in equivalent units of pressure, and then do the factor conversion. There will be an opportunity in some of the training programs to practice this mathematically. However, the concepts are important here. Volume. Units of measure of volume are fairly familiar. A litre is 1,000 milliliters. A milliliter is 1,000th of a litre. A cubic meter, though, is 1,000 liters. So, if it's water, it would actually weigh a ton. That's relevant because hyperbaric chambers, for instance, are often measured in cubic meters. In the United States, diving cylinders are frequently designated in cubic feet, and 1 cubic foot represents 28.3 liters. That's simply a unit of measure that's useful to know. Temperature. As mentioned previously, the common temperature scales are relative or gauge scales. This is illustrated easily by realizing that 0 degrees centigrade or 0 degrees Fahrenheit is not as cold as it can get. We frequently have minus degrees on the weather channel. So it means that it would need to be adjusted by a certain amount to be an absolute temperature. If we imagine this to be a continuum from zero kinetic energy, which molecules would theoretically stand still, to infinite kinetic energy, then the centigrade and Fahrenheit scales are somewhere along them. So, in order to convert these scales to an absolute scale, we need to add 460 units to Fahrenheit to produce Rankine, which is absolute temperature, or to add 273 units to the centigrade value to arrive at Kelvin, which is its absolute equivalent. To show you the impact of doing this, let's imagine we have a gas that is at 5 degrees Fahrenheit and it is heated up to 50 degrees Fahrenheit. Now, if we were to use a simple factor conversion, we would see there's a tenfold difference or 1,000% difference between the two. But if we consider that on the absolute scale, we would see that we need to add 460 to the 5 and arrive at 465 Rankine, and then 50 to 460 to produce 510 Rankine. And this is only a 1.1-fold or a 10% difference. So it's easy to see how one would make enormous calculation errors when using relative temperatures rather than absolute temperatures. So always use absolute temperature in calculations. These are common formulae to convert Fahrenheit to Celsius or Celsius to Fahrenheit. Now that we've considered the variables, let's look at the actual laws. As mentioned earlier, there's the ideal and general gas law, and then the derivatives of the general gas law, Boyle's, Charles, and Gay-Lussac's law, followed by Dalton's and Henry's law. I've provided you with a framework within which to contextualize the various gas laws and derivatives of the general gas law. I hope it'll make it easier to understand how they relate to each other. We'll get to the ideal gas law a little bit later, so let's just start with the general gas law. The general gas law, as you'll see in a moment, compares the same gas in two different situations, of which, typically, one of the three variables is going to be constant. So, given then that the number of molecules is not changed, which is the requirement to use the general gas law, the only remaining variables are pressure, volume, and temperature. If it is pressure and volume that changes, while temperature remains constant, that is Boyle's law. If volume and temperature change whilst pressure does not, that is Charles's law. It might be useful to remember that Charles was actually the inventor of the hot air balloon, and a hot air balloon, as you know, actually has an opening at the bottom, so it cannot sustain pressure. It's always open to the environment. So the pressure will not change in a hot air balloon, and perhaps that will help you to remember volume and temperature as being the variables. Some of you in dive training may have been taught about Charles's law of constant pressure and Charles's law of constant volume. This is obviously from a teaching point of view to make it easier, but also because Gay-Lussac was one of Charles's students. And Gay-Lussac's law is in fact the same as Charles's law of constant volume, because Gay-Lussac's law considers variability of pressure and temperature in a constant volume. You'll see examples of this in a moment. So, let's start off then with the general gas law. The general gas law is derived in the following way. A volume of gas will vary inversely with absolute pressure and directly with absolute temperature. So, using mathematics, we can see that pressure and volume over temperature represents a constant factor, and that constant is subject to the gas molecules not changing. In other words, as long as the number of molecules that represent the particular pressure, volume, and temperature don't change, the constant won't change. As a result, if we have a gas that is exposed to two different situations, but the actual number of gas molecules don't change, we are able to solve that as long as they don't, the pressure, volume over temperature in situation 1 will be equal to the same constant as the pressure, volume, and temperature in situation 2, and therefore we can simplify it in this way. And that's the general gas law. Now, when we break this down into the derivatives, all we essentially do is to remove one of the three variables as they then become constants. In other words, they too do not change in the two situations. Now, the important thing to remember is that the general gas law is only applicable when there is no change in the number of molecules. So again, it is critical to remember that the absolute values must be used for temperature and pressure, that we must determine whether the number of gas molecules have changed or not. If they have not, we can start with a general gas law, and that we need to label and use the same units of measure throughout. Those are key. Now, what do we do if the number of gas molecules actually have changed? And as an example, let's imagine this situation of a compressor filling gas cylinders and the gas cylinders heat up. whose law applies here? Well, intuitively, some of you might think that this would be Gay-Lussac's law. The volume is constant, and it's a pressure-temperature situation. However, remember that Gay-Lussac's law is a derivative of the general gas law, and here we have been adding gas, and therefore this is not a factor of the general gas law. It is in fact heat of compression, or otherwise called the Joule-Thomson effect. Do not be misled into thinking of this as either Charles's law of constant volume or Gay-Lussac's law. This is an effect of compression. Getting back to my previous question, when do we use the ideal gas law then? The ideal gas law is rarely used in diving calculations. Nevertheless, what we're doing with the ideal gas law is to narrow down the factors that are encompassed in the constant that we derived just now when we looked at the relationship between pressure, volume, and temperature. The constant is in fact made up of N, which is the number of molecules in moles, and R, which is otherwise known as the universal gas constant. In other words, all we're doing with the ideal gas law is allowing ourselves to quantify the impact of a change in the number of gas molecules. In the general gas law, the only variables were pressure, volume, and temperature. So, solving for this constant, we can now say that pressure volume equals number of moles times gas constant times temperature. And that's the familiar way in which the ideal gas law is written. Dalton's law. Dalton's law states that the total pressure exerted by a gas mixture is equal to the sum of the partial pressures of each of the different gases making up the mixture. So, if you imagine that graphically, you can see that the total is equal to the sum of the parts. But this is rarely how we use Dalton's law in practice. In practice, Dalton's law is actually used by adding Avogadro's law. Avogadro's law states that a given number of gas molecules will occupy the same space. As a result, we can say that the partial pressure of a gas is in the same proportion to the total pressure of a mixture as its number of molecules is to the total number of molecules. If that's too complicated, basically we can say that 20% of a mixture will make up 20% of the pressure. Now, what we need to remember is that gas percentages as such merely indicates the ratio between the number of gas molecules. If I were to give you 100% oxygen in the vacuum of space, it would be meaningless. And in fact, if I were to give you 1% oxygen at 700 meters, it would cause oxygen toxicity. So the percentage is merely the means by which we can calculate the physiological impact, which is subject to partial pressure. So the important factor is really partial pressure, and percentage is merely the means whereby we are able to arrive at calculating the partial pressure. One of the privileges I had during my studies was to spend a year under a research and clinical fellowship at Duke University's F.G. Hall Environmental and Hyperbaric Medical Facility. This is one of their experimental chambers in which on the 3rd of February 1981 they conducted a world record dive to 686 meters, which essentially is 70 atmospheres. Anyway, at 70 atmospheres, to give those aquanauts a PO2 of 0.35 atmospheres, which would represent 35% oxygen at 1 atmosphere, the gas mixture had to be diluted down to 0.5% of oxygen, because 0.5% at 70 atmospheres is 0.35 atmospheres absolute. A simple way to manipulate these different variables, the fraction of a gas, partial pressure, and ambient pressure, is by means of the diver's T. And essentially, to determine whether a particular gas would be toxic or therapeutic, one would then multiply the fraction of the gas, which is a decimal version of the percentage, by the ambient pressure. To determine whether a particular gas mixture is ideal for an application, you would divide whatever the target partial pressure is by the ambient pressure. And similarly, if one needed to determine whether a particular gas would be usable and to what depth it would be safe, one would divide the partial pressure, which is the target or threshold of toxicity, by the fraction of the gas. Now Henry's law. Henry's law states that the volume of gas that dissolves in a liquid is proportional to its partial pressure. In other words, if you apply pressure to a gas in contact with a liquid, additional quantities of that gas will dissolve into liquid until it reaches a new equilibrium, where the same number of molecules entering the liquid will start leaving the liquid. So, the concentration of dissolved gas is a function of the partial pressure. Just to make this a little bit more real, we as humans breathing air, which is 80% nitrogen, at 1 atmosphere, would actually dissolve approximately 1 liter of nitrogen. At 2 atmospheres, over time, this would become 2 liters. At 3 atmospheres, 3, and so on. It does take time, though. In other words, it would require an equilibrium to be reached, and that is a function of breathing and diffusion. On the topic of dissolved gas in liquid, let's consider the difference between partial pressure and gas tension. As physicians, we often use astrip or blood gas interchangeably. The partial pressure and gas tension is expressed in the same units of measure, usually millimeters mercury or kilopascals. But from a physics point of view, a gas tension is gas molecules that are dissolved, whereas partial pressure is free gas molecules. Why is that important? Well, it's because when you apply pressure to a system, gas tension and partial pressure behave differently. Using this model as an example, if you increase the pressure of a gas in contact with a liquid, the partial pressure increase will result in an increase in dissolved gas tension. So an increase in partial pressure will result in an increase in gas tension, but it will take time. However, if you look at this model and you apply pressure to a liquid containing gas that is already dissolved and there is no gas in contact with the liquid, it's all dissolved already, as you might find, for instance, in our physical tissues, then the pressure is not going to be adding additional molecules. There are no molecules to add at this level. So let's take that concept to recompression. This is tissue, you've got dissolved nitrogen and a nitrogen bubble. As pressure is increased, the partial pressure in the bubble will increase, and it will tend to then move from the bubble out into the surrounding tissue as a function of the increase in partial pressure. And that is how bubbles are collapsed using recompression. The reason why we are able to do this without adding appreciably to the dissolved nitrogen is because it takes time for the dissolved nitrogen to accumulate from the lungs and the circulation. So in a way, the dissolved gas tension depends on partial pressure, and specifically that of the gas in contact with the liquid, which is Henry's law, whereas gas bubble partial pressure will depend on the ambient pressure, or Boyle's law, and therefore Dalton's law. So in a way, recompression is beating Henry with Boyle. You are able to reduce bubble volume before dissolved gas accumulates. Let's look at Laplace's equation. The pressure in a sphere increases as the radius decreases for the same surface tension. In this case, we're referring to water and a bubble. The practical implication is that as bubbles become smaller, they tend to collapse on themselves, whereas as they become larger, they tend to grow. Poiseuille's equation is also fairly obvious. Consider drinking yogurt through a straw. What would the ideal straw be? Well, short, wide, and of course, you would apply a certain amount of force. An additional factor is the thickness. You could dilute the yogurt. So, looking at it graphically, the flow through a tube depends on the pressure gradient, in other words, the delta P, or the difference between P1 and P2. the radius of the tube, the length of the tube, and the viscosity of the liquid. As a formula, this is how it would be written. Note that the radius is the most important variable because it is to the power of 4. So a small change in radius would have a tremendous impact on flow. And that's why asthma may produce problems with diving. Pascal's principle. Pascal's principle relates to the transmission of an applied hydrostatic pressure to a liquid. The pressure exerted at any point in a confined liquid is transmitted equally throughout. This is relevant in body tissues that are affected by ambient pressure changes. However, the ones that are really important are those that have air-gas interfaces, because the gas is compressible. This is a graphic depiction. As the plunger is injected, the water sprays equally in all directions as the pressure is transmitted equally throughout. Imagine, if you will, a confined liquid in the body adjacent to a gas-filled space, for instance, the inner ear versus the middle ear. If the system is pressurized, then there will be a gradual collapse of the gas system, whereas the liquid portion will not be changed, but there will be a tendency of the liquid to ooze, squeeze, rupture, or bleed through into the gaseous space. And that's what we find with middle ear barotrauma. In fact, you can simulate that by just sucking on the back of your hand. Hyperemia that develops is as a function of Pascal's law. Pressure is exerted equally throughout, except between your lips and the hand, where you've created a lower pressure. An extreme form used to occur in the old days of diving when divers lost their supply to the surface prior to the introduction of a one-way valve. Divers would literally be squashed into the helmet. A more practical application today would be these subconjunctival hemorrhages as a result of an individual diving with a mask that they did not adjust to pressure. A quick question: would blood pressure change with changing ambient pressure? Well, notwithstanding the effects of exercise perhaps or immersion, the blood pressure would not change because, remember, the ventricles would still pump the same net additional pressure over and above the ambient pressure. So we don't change into an amoeba when we start diving. The pressure is transmitted equally throughout. The last important component of physics is common sense, and what we've really done is just adding to it. We've reviewed buoyancy, gas laws, Laplace's equation, Poiseuille's equation, and Pascal's law.